We'll start in about half a minute when just make sure the recording starts for the students who are not here. Any questions so far? Oh, today's first tutorial, how did it go? I guess half of you were there, yeah? Okay, good. Yes?
Is the rule that no assignment, like programming assignment questions can be discussed on Piazza?
No. You could discuss. We have a TA who monitors questions about programming assignments.
I see, because the TA, I tried to answer a question, I thought I was helping without giving the answer, and the TA
Oh, you mean the students giving answers?
Yes.
I see.
Just got talking, there's a question on Piazza. I just want to, I thought it was okay if I wasn't giving something away directly.
Yeah.
So I just wanted to confirm that.
That's a good point, yeah. I guess it's up to the TA to judge whether you are giving too much of an answer or not. So just be a bit cautious, I guess, yeah. Yeah. Oh, yeah, it is a common place for students to discuss with each other, yeah, good, yeah. Anyway, let's get started. So today we are talking about, we're going to cover a new learning method called logistic regression, okay? But before we start, go to the meat of logistic regression, let's do a bit of a recap about what we have seen already, which is linear classification and linear regression, okay? And then we're going to make a comparison between these three different methods. So again, we have the n data points in the training set. So far, we have this form of an unknown target function that we want to learn about or want to estimate, which is y equals to f of x, like that, right? And then we say, well, we are choosing the best function to approximate this f from a set of hypothesis functions. And essentially, that's what we're looking for, right? Where h is within the hypothesis set. Yeah, we're choosing the best function among the set of hypotheses. Yeah? And then we call that y hat. That's our estimation for the label y, right? So, and there are two methods so far. Linear classification. And we have x, the input being a d+1 vector. The output, well, for now, let's say it's a -1 + 1, let's say. Binary. It could be other values in general, as long as it's discrete, right? And in the binary case, we use a sign function of the inner product between w and x, which is essentially a weighted sum of the features within the vector x. Yeah, it's a weighted sum of the features inside x. Okay, and then you use a sign function to threshold. Yeah, and then you decide whether y hat should be plus or minus. So we can use a picture to represent this. We can draw our perceptron, right? x0, x1. These are the features. Yeah, maybe xd. This one comes in, multiply w0, right? Yes, yeah. I'm using my own right now. I'll replace it. Thank you. And we sum them all up. Right? And this is w1, of course. D, right? And we're going to give a label. We call this S. Yeah, just for convenience, that we will use later, right? And then after that, what do? We send it to a sign function, right? And let's draw a sign function. I'm going to blow up this node a bit. Yeah, a sign function, of course, looks like this. Negative side is -1, and then positive side is +1, right? That's a sign function, just a step, a jump. And so with that, your output y hat, of course, is a sign of S. like that. Okay. Let me save my backup battery so next time. Okay. And for linear classification, we define an error function. Right? This is the error per sample point, which is basically counting how many, whether there's an error or not. Right? So this is an indicator function. Y is not equal to sign of S. Yeah. So far so good. We have seen this, and then we also studied linear regression. Again, we have the same input, d plus 1, this augmented vector. And then, but the output is simply a continuous real number. And a y hat is simply the weighted sum of the elements of x, right? Just the inner product. So how do we draw a picture to represent this? Well, we do the same thing. In fact, I'm just going to copy and paste this whole thing. Hopefully it works out. Copy, and then you can paste it. Because it's exactly the same. The front end is exactly the same. Yeah? So the difference is simply what this node is. Yeah? This circle in the language of neural network later is also called the activation function. Yeah? So the activation function for linear regression would be what? What does it look like? The output y hat is simply equal to S, right? So what does that activation function look like? Yeah, x equal to y, so just a diagonal line, that's all, right? Diagonal line. Just like that, yeah, going through the origin, yeah. So if you compare the two, you see the difference, right? That's the only difference between these two, really, right? The activation part. And you see that logistic regression also will make a difference of the activation, and that's all. The rest is the same, okay? But before I go there, let me just also write down that for linear regression, our error definition is the square error, right? This is the error for each one of the sample points. Yeah, so far so good, right? Now, you notice that here we are trying to estimate the function f. Yeah, it's a deterministic. Yeah, and we are finding this a deterministic form to approximate another deterministic function. Yeah, so everything above we have a deterministic hypothesis. Okay, so everything above deterministic. Let's say hypothesis H. Hypothesis H. Yeah. But in many real systems, you might not want to be so sure, so deterministically, that this is a 1, this is a 0. Okay. One example, maybe you are a doctor. You want to diagnose whether a patient has the flu or COVID or whatever. Yeah. You might not be so sure to say that this is exactly, +1 flu or not. Or you may want to say, well, this is with a high probability it is the flu. Okay? So, and that's when logistic regression comes in. So in the case when we want a random hypothesis, randomness in H. Yeah? Okay, so this is now we're going to the new stuff. A quick example, let's say the input, maybe a patient, or any person, in fact. Let's say the average fat and sugar in this person's diet. Yeah, you can say per year, per day, doesn't matter. Yeah? The details are not important. We are not real doctors here. Yeah? Let's say the output is heart attack. Again, could be heart attack within the next 10 years, heart attack within the next year, and so on. Yeah? Details are not important, but that's the label that we want to assign to this person based on what kind of food they eat. Yeah? So it's very hard for you to really make a deterministic conclusion to say that, well, you eat this much fat and this much sugar, you definitely get a heart attack, right? No matter how many years later. Yeah? It's very hard to make this deterministic conclusion. Yeah? So we will almost always want to make this more of a soft decision to say, well, if you eat a lot of fat, a lot of sugar, you have a high likelihood of getting a heart attack. Yeah? So how do you express that in that case? Yeah? How do you express this kind of hypothesis? So we want to say, again, maybe depending on the proportion of fat and sugar, right? Then there's a weighted sum. Yeah? So therefore, again, a large weighted sum of these two items leads to a high likelihood, more likely, that y is +1. Yeah? Okay, make sense? Yeah? So now, exactly what are the weights of fat and sugar? Well, it depends. Now, that's something that you can maybe use historical data to compute, right? Yeah? But in general, we would like to have this kind of statements. And what we have seen before, logistic regression, I'm sorry, linear regression and linear classification does not do this. Yeah? Everyone agree, right? Those are deterministic hypotheses. Now we want to have a random one, probabilistic one. So we have defined a new target function in this case, right? Yeah. Which is probabilistic. So let's call it fp of x instead of just f of x. Yeah. So let's just define it as the probability that y is +1 given this input x, the features. Okay. This would be our new target function. So this is, of course, it's a soft decision, right? Yeah, instead of a hard decision in linear classification. Okay. And in order to estimate and predict this type of soft target functions from our data, we need this new tool, this new learning method called logistic regression. Now, this is a learning method, right? So we have seen from the other two learning methods before that to describe learning method, you have to describe the training data set, the decision rules or the set of hypotheses, and then you have to decide the error function that you want to minimize or the loss function that you want to minimize, and then you want to describe maybe a learning algorithm to minimize that loss. Yeah, and we have to describe all of that in order to describe logistic regression, right? Okay, so let's start. The data set, well, the data would be, again, we look at a augmented data form, so D+1 dimensional data. Why? The output is still -1 and +1. Okay, so we are still, at the end, the labels that we get from our training data is still heart attack, not heart attack for this patient. Okay, these are our data points. Okay? We don't get probabilities for data points. Yeah, even though this is generated from the probabilistically, these are generated randomly. Okay. So we have turns out that the front end of logistic regression is the same as what we have seen before. So I already have this in my memory, so I just paste it over here very nicely. Yeah. So like that, we send it to a new activation. Okay. What we want to output is a probability. Yeah, right? We want to output a probability to say that this data point is likely to be a plus or likely to be a minus with this probability. Yeah? So to output probability outside, so probability has to be between 0 and 1, right? And it's continuous between 0 and 1. So what we expect as output has to be continuous between 0 and 1. If it's continuous, then it is regression. Not cosmic. That's why we call it regression. Okay. There's also logistic because this is not exactly linear regression, right? Yeah. Okay. So we want something that looks like this because it's a probability. Yeah. We want to map something that's between 0 and 1. So I'm going to blow up this curve a bit below. Okay. So right now, just roughly know that there's this kind of shape like that. Okay. In fact, we're going to use this function theta s equal to es 1 plus es like that. Okay. This is called the sigmoid function. Yeah. So theta s is the called sigmoid function. Sigmoid basically means it's S-shaped, as simple as that. Yeah. Nothing mysterious about this term. Yeah. It's an S-shaped function. It's a fancy way to say it. And if we draw this out a bit more, so you have S here, theta s in the y-axis. It has an asymptote of 1. Yeah. And at s equal to 0, what is it? When s equal to 0, what is theta? Yeah, half. Yeah. Oops. Where does it go? Yeah. So it's symmetrical, turns out. Yeah. Symmetrical left and right, and up and down as well, but around half. So it looks something like this. This is saying asymptotically goes to 1, and this one asymptotically goes down to 0. Okay. Like that. If you plot this, you can do it on your calculator or MATLAB easily, right? Yeah, or Python. Okay. And basically what we're saying is that this would be our guess for the probability, right? Our guess for the probability we want to see. Remember our objective function, right? That's what we want. The new target function is the probability. Yeah. Basically now we're saying that this is our guess for that probability. Okay. So therefore our hypothesis or our learning model, if you want, or our decision rule, if you want. Yeah? All different names, they all mean the same thing. Yeah. I'll just write model, the logistic model. Oops, it's a probability that y is equal to plus 1 given x is equal to theta of s. Yeah. And of course, we know that this is simply theta of w x like this. And if you substitute this inside the theta s, this is simply e to this 1 plus e. It'd be messy, right? Starting to have fractions, and then within the fractions you also have exponents. Yeah. And by the way, there's this is one of them. This is actually only one example of a sigmoid function that gives you a probability between 0 and 1. Okay. In some applications, especially in neural networks later, you actually might want to have an output that's between -1 and 1. So you capture some negative side. You're not outputting probability, but you're outputting something else. Okay. So another example of this, just as a aside, yeah, another example of a sigmoid function is that a so-called hyperbolic tangent function, es plus, minus here above. And then it's hard to draw a straight line when I'm standing up like that. Okay, you're going to see this guy quite often in neural networks. But we don't worry about this one for now. Okay. Let's focus on our sigmoid function of that form. Yeah, the one that goes from 0 to 1. Yes. Yeah. Mm-hmm. That would be this one. Yeah, that's exactly the same. Yeah. Okay. Yeah. Yeah, they're the same. Yeah. So let's look at this, our theta, our sigma function, and make some observations. First of all, I would like to show you the geometry of this function. Well, you know what? Yeah, geometry of this function. At least for D2, yeah. Higher dimensional, it's very hard to visualize, but at least D2 we can see it. Yeah. So let's do this. Let me see something. I feel like. No, I think I have everything. Okay. X1, X2 over here, like that. Suppose I have this line. This is defined by W transpose X equal to 0. Okay. In linear classification, this would be the boundary, right? To say that one side is plus, the other side is minus. This is a deterministic boundary for linear classification. Yeah. In particular, people also often put a arrow like that to indicate this side is the plus side. Yeah. The other side is the negative side. Yeah. So in fact, this indicates side of positive this product. Yeah. Or in fact, it's same as saying that y is equal to +1, right? For the case of linear classification. Yeah. By the way, you can specify that side as positive as well. It's not true that above is always plus, right? Below could be plus, depending on how you define your perceptual. Okay, be very careful about this. That's why you always have to draw an arrow to indicate that that's what I mean. Up is positive or down is positive. This one also happened to, for those of you who are comfortable with linear algebra, this one is also pointing at the direction of W1 and W2, that vector. Okay, this is same direction. As not the whole W, because the whole W is augmented. It's a three-dimensional thing, right? So this is only W1, W2, the two-dimensional one. Okay? If you don't quite understand why, that's okay. Don't worry too much about it. Yeah, just know that this arrow indicates plus. That's good enough. So if this is a division line, now we have two parts. Previously, these are just minuses, and that side is all pluses. But in logistic regression allows us to talk about how far away you're from the line and how close you are to the line. Okay? If you're close to the line, the inner product will be small, right, in magnitude. Is that right? When you're close to the line, because on the line, the inner product is 0. Yeah? When you're far away, that product, the inner product, has a larger magnitude, right? So let me write it. Let's say here you have this side, you have small magnitude of that, and up there you have large magnitude. Likewise, below is the same, right? You have, when you're close to the line, you have small magnitude of the product, and then here you have large magnitude of the product between the two, right? Yeah? And in the middle, it's just 0. Yeah? That's large positive, small negative, large negative. Okay? Now, if W transpose 6 is positive large, then what is our theta value? What is our estimated probability, our guess, for our hypothesis for the probability? Yeah, nearly 1, right? Because when it's infinity, you remember your calculus, yeah? When this infinity, then infinity divided infinity is actually 1 over there, yeah? So here our theta is actually approximately 1. Because this is large positive, okay? Here, when we have large magnitude but it's negative, what is theta equal to? In this one, what is it? 0, right? It's negative, and then you get a very small, and then 0 divided by 1. Yeah, so you get approximately 0 probability. Is that a good thing or bad thing? Yes. Again, be careful. We are not looking at this guy. Okay, we're looking at the one above. Yeah, our own theta. Yeah, not 10. Yeah, yeah. We're looking at our own sigmoid function, not the alternative. Yeah. So, does this make sense that far away from the line, this one roughly is 0, the other one is 1? Remember, this theta is our guess, our hypothesis for the probability that the label should be plus, right? Our hypothesis for the probability that the label is plus. Yeah. So if it's large, when we're far away from the line, we say it's more likely to be a plus above, right? When it's below, we know that this side is supposed to be the negative side, right? If you're far away from a boundary, of course, you want to say that it's more likely to be negative, yeah? When you are close to the line, say, well, I'm not sure now, okay? Yeah? When you're close to the line, you're not sure. But when you're far away, you're pretty sure this is -1. That one is +1. Yeah? Everyone okay with that? When you're far away above, this is the probability that is +1, right? This is the probability that is +1, but the probability +1 is 0, means that the probability is -1 is 1. Yeah? So these regions far away from one, you're very certain about your decision. Yeah? But when you're near the border, you're not sure. Okay? This, as opposed to linear classification, when you just say, that's the line, I'm very sure, but just everything above is plus, everything below is minus. Here, we're saying that, well, we have the line here. If you're close to the line, I'm not so sure, but you're far away from the line, I'm very sure that this side is negative, that side is positive. Okay? So, this is a soft threshold for the likelihood. Instead of a deterministic threshold for just the label itself. Yeah. Second thing, I mentioned a little bit already, that there's this complementary probability, right? If we'll define the probability for y is +1, but what about y is -1? Yeah, just 1 minus that, yeah, just a simple probability. I already mentioned that probability is very important to this course. So this kind of basic probability you definitely need to know. Yeah. So this is equal to, come on, okay. Equals to 1 minus, well, just substitute our formula for the probability, right, like that. And then in that case, we will get 1 over 1 plus this guy, yeah. And well, let's do one more step. We divide EW transpose X again on numerator and denominator. Then we have E minus W transpose X. And then here is 1 plus E minus W transpose X, right? Yeah? Why do we write it in this form? It should be obvious. Now this is just theta of minus W transpose X, yeah? Yeah? And of course, this is simply theta of S. Oh, I'm sorry, minus S, of course. Yeah? So it turns out that the probability of y is -1 simply is theta of minus X in this hypothesis. Yeah? And this is the so-called logistic regression hypothesis. Yeah. It has this nice property, nice kind of a symmetrical form. Another thing to note is that we're going to, in order to carry out our analysis later, we're going to introduce a new notation for our hypothesis. That just to indicate that this is a function, our hypothesis is a function of W, right? Because the hypothesis really circle around the line that we have before, right? tilde line defined by our w. So 1 given x like that. Okay, we define this. We simply it's this one, right? That's our guess for the probability, right? We just write it out so that it's clearer that it is this one is the probability for y equal to 1, and then it is a function of w. And w is something that we have to optimize later, right? We optimize w to minimize the loss function. Yeah. So this is our estimate for the probability that y is +1 given x. Yeah. Yeah. And of course, we correspondingly we have this one as well, -1 x is equal to theta of minus like that, right? Just the estimate for y is -1 given x. Want to write it out this way because now we can combine the two of them together. I can replace this by a general y. The y can be either +1 or -1, right? Just a label. Now you see, only changes the sign, right? So I can write it as theta y times w transpose x, like that. Where have we seen this before? Yeah, where have we seen this before? Yeah, the PLA, the perception learning algorithm, right? When we explain why it works, yeah, in an intuitive way, okay? So this guy shows up quite often, yeah? So that's why it's an important form in this type of linear learning. Yeah. So let's write out one more step, actually two more steps. So this is equal to E y w transpose x, and 1 plus E y w transpose x. Of course, just to make sure that we have this y is -1 + 1, right? Otherwise, it would not work. So this is 1 over 1 plus E minus y, like that. Okay? So this is just a redefinition of some notations, that's all, right? Nothing new here. We're just relabeling things, and it turns out that we have this very clean-looking form for our prediction of the probability. Yeah. So now we're done with our model, our hypothesis. What about the loss or the error function for this method? Yeah, how do we define the error? One, something that we have to optimize, right? The criterion for our optimization. Okay. So again, we have to define the error for each one of the sample points. Yeah. So therefore, for the nth example, in the training data, of course, later you can also use the same error criterion for testing data as well. Yeah, it's called EN. It's of course a function of the choice that you make, which is W. We define a funny-looking error. It's a log of this probability. Okay, yn given xn, like this. This log here is a natural log, first of all. Yeah, so this natural log. Also, another thing to note is that this is sometimes called a log loss function. Yeah. We take the log of a probability. Okay. Fortunately, probability is always from 0 to 1. Yeah, so you can always say log unless it's 0, then it's minus infinity. But at least it is well defined everywhere. And why do we have this log form? We will discuss next time in detail. Yeah, but today we just look at some numerical examples and see why this one makes sense. Why it's an interesting and useful error measurement, error criterion. Okay. So for now, let's just go back to this function, this probability, right? This p hat there. So when you take the log of this guy, 1 over, then you have a negative coming out of the log, cancel out with this negative very nicely. That's why we have a negative sign in front, right? So now if you substitute that in, you have log of just 1 plus e minus y w transpose x like this. Okay? I should say yn xn. Right? This is the nth. Yeah. Okay. What does this look like? If we plot this, S, of course, S is the this inner product, right? Yeah. Well, what does it look like? Well, it is a log of a 1 plus e something. It depends on, it's so it's depending on what yn is. So depending on whether this exponent is positive or negative. Yeah. So if it's positive, if it's let's say positive, yeah. So then you have, let's say, let me write it here. If yn is plus 1, yeah, then we actually have log of 1 plus e minus s. Okay. Yeah. So when e minus 1s is very large, asymptotically goes to 0. Yeah, but then looks like this, I guess. Yeah. Okay. And likewise, if yn is negative 1, what does it look like? Now this exponent becomes plus, right? 1 plus es, so it goes up like that. Yeah. So nice form like this. So this is the case if yn is negative 1. So you have log of 1 plus e plus s like this. Okay. Now, one thing to note, let's look at the extreme case. So we know the two sides. The extreme case, if this is much greater than 0. So the s is much greater than 0. And yn is plus 1. The true label, remember, yn is true label. Then what is the loss in this case? Our en, yeah, is the loss. Yeah, equal to 0. Yeah? So when this is very much greater than 1, that means we are, based on our hypothesis, we're very confident that it's plus 1. Yeah, we're very confident it's plus 1. And then if the true label is really plus 1, then you want the loss to be 0, right? There's no loss because you make a right prediction. Yeah, that makes sense. And on the other hand, if this thing is much less than 0, so on the very negative side, and also happen that yn is minus 1, the loss should be also 0. Yeah, and that's exactly what we observe from those curves. Yeah, that side, both sides, asymptotically they're 0. So this is good for at least for the extreme cases. We are doing good. Yeah, we're doing well. Right? So now let's look at some examples of more intermediate results, not asymptotic results. Yeah. Let's say, suppose you have you run your logistic regression. Suppose you have a way to solve that problem to minimize this this en, and of course you define en and then minimize it. So suppose we'll talk about how to solve it next time. But for now, suppose you can solve it, and then you find the optimal solution, and you get this logistic regression solution. Let's say output, let's say, yeah. W. I'll put a line for you such that let's do a bit of an extreme case first. Xn is equal to 0.999. Okay. So you're very confident that for this particular data point, it should be plus 1, right? You're 99.9% sure it should be that, +1. That means also that you are saying that it is -1, you're guessing it's -1 with probability 0.01. Yeah, they mean the same thing. Yeah, so you're quite certain that it is +1. Yeah. So therefore, let me write it down. The machine at this point, machine is very, very sure. Yeah, confident. Let's say confident that the estimate, the y hat n should be 1. Okay. So in that case, if that now you look at your data set, the real rate label, right? If in fact the true label is +1, then what is the error for this data point? Well, we substitute into our log loss function, yeah, a log loss. So it's a negative log of basically this probability, right? So 0.999. Okay? And, well, what is that equal to? If you, very small, yeah, not really exactly 0, but turns out to be, what happened to my pen? 10. Oh, come on. Okay. 10 to the -4 turns out, okay, roughly. What if you're unlucky? The data point that you get actually is a -1, yeah? So this line that you give may not be such a good line, right? So what is the error for this data point in that case? Yeah? Yeah. Turns out to be 10, roughly. Yeah. This natural log, remember, this natural log. So just like roughly, yeah, it's a big number. Okay. So you see that when you make a mistake, pretty much, right? When your output W is bad for this data point, then for this data point, your loss value is very big compared with the case when you are correct. And of course, you can say, what if I have an intermediate case? Let's further suppose another case. Yeah. Suppose now you're not so sure. You have this +1 is 0.8. Yeah, that means -1, 0.2. Yeah. So that's your W, right? This another line. For another line, the same data point. Let's say if the data point is a +1 label, turns out, yeah, then the error, again, plugging in. Now you plug in 0.8. Yeah. So it turns out to be 0.22. Okay. And if yn equals to -1, E in now you plug in the one with negative, right? So 0.2. Yeah. Roughly, should it be bigger than 0.22 or should it be smaller than 0.22? Why? Bigger or smaller? Okay, yeah, just from purely number way, yeah. But let's just say from just conceptual way, right? Your guess says that, well, I think this is more likely to be +1 than -1, right? I'm 80% sure that it's +1. Yeah, I'm only 20% sure it's +1. If it turns out to be, your guess is actually wrong, yeah, because you're saying that 80%, right? So you should have a higher error in this case. So it should be higher than 0.22, yeah? So you know it should definitely be higher than 0.22. So it turns out, yes, it comes out to be 1.61. Okay? So I hope I convinced you how this log loss function works. Okay? we are not talking about why yet. What is the mathematical reasoning behind it? We're going to talk about it next time. Yeah, but for now, numerically, it seems to work very well. So in that case, then, to summarize the logistic regression, what we are trying to do is to collect all of these errors among your training data, right? So given your training data set, yeah, we want to find the W. In other words, you find the boundary line. Yeah. But we don't minimize the number of errors, like in linear classification, but rather we minimize this loss function. So the average of EM W like that. Yeah. And if you will, you can write this down as because each one of them is just that log form, right? N equal to 1 to N log of 1 plus E minus YN W transpose XN, like this. Okay? So for the first part, we're doing exactly the same thing as linear classification, right? Binary linear classification. But then we change the error criterion to this logistic regression criterion. That's all that we're doing, right? Instead of counting the number of errors, we're taking this probability form, this loss form, okay? And we know why is this maybe better than the linear classification form? Why is it better? It allows you to say, well, if I'm close to the line, then I'm not so certain. If I'm farther away, I'm more certain. Yeah, it allows you to say, remember the margin issue, right, that we talked about last time, yeah, before, okay? So this is one to give you a more precise description of how certain you are about things. Okay? And usually this form allows the machine to learn better from the data. Because in reality, data almost always have some noise. Yeah, it's almost always random. Yeah, that's why this form usually works better. Okay, and yes.
Could you go back to the graph of the error that you drew earlier?
Yes.
That's not exactly exponential, right? Like as it goes big.
Yeah, the log would I think it would go to a flat.
Right.
Yeah.
Linear as it goes off.
Yeah, that's right. Yeah. But usually we don't care about those parts anyways. Yeah. Okay, so we'll meet again tomorrow. Yeah.
I don't know how it happened, but when I was registering for the course, I didn't